This is Dan again, and I'm here with Olaf the Loaf Dog sleeping. I want to go back over the last video. I want to make it a little bit more concise. And what I was trying to get last time was simply that you have classical ways of compute where you treat bits as, two distinct places to be. So there's a zero over here maybe and a one over here. And then your point is your value is somewhere in between these two. And you can see that like as I get closer to one, the probability that I read out a one is increased, and the probability that I read a zero is increased as I get closer to zero. But for most classical compute, we're just stuck at 0 and 1. So we're not just getting close, we're just stuck at 0 and 1. But there's another way in which you can do compute. There's actually many ways you can do compute, but for our purposes, the other way that you can do compute is to put 0 and 1 on orthogonal axes. And then your state, instead of being a point between the two, it's now a vector between the two. And that vector, the angle that you have with a 0 is what the probability that you'll read out that 0 is, and the probability that you read out that 1. However, we haven't actually broken away from classical compute yet. This is still a paradigm that just gives you classical tractability. It may be a little bit harder to represent on our current computers, but it's classical. There's nothing special about it. What makes it quantum is the fact that there's this idea of duality in quantum, and each one of these axes, these orthogonal axes, has a real and an imaginary side to it. And that real and imaginary side to it are also orthogonal axes. So every axis, the 0 and the 1, has a real and imaginary. So it's a real 0, real imaginary 0, real 1, imaginary 1. And that's 4 different axes, and they all have to be orthogonal to each other. This gives you a 4-dimensional object, or a 4-dimensional space, in which your vector, there's only one vector still in it, is described by its angle to all 4 of these axes, and that gives you your qubit. Of course, since your probability is always sum up to 1 that you'll either read out a 0 or a 1, the length of that vector is generally of unit length 1, which means it's actually a unit sphere or a unit hypersphere. Representing the hypersphere is very difficult in our brains because we like to think in 3 dimensions, and we see in arguably 3. And so what ends up happening is that we create representations of this, which tends to be a block sphere, B-L-O-C-H sphere, which is a 3-dimensional projection of a 4D sphere. And we can describe the state pretty well for a single qubit on that. And I think it's a little bit more of a concise explanation, so I'll leave you with that today. All right, have a good one.